Hello and welcome back to Calculus 1, section 5.2 on definite integrals. All right. Is this going to be different than what we learned? Well, somewhat. You already know integration, hopefully. 4.9 introduced you to the idea of antiderivative, which we also call the integral. And we found out that if you integrate, you get to put that plus c and you are done. So an example would be, let's say you have integral of 3 over x squared plus 1 dx. Well, you kick your constant 3 outside, and then you have integral of 1 over x squared plus 1 dx, and this is what? Very good. So, and then you have to put plus c at the end. So this was one of the basic integrals, and we had this little twist with number 3, which is a constant, and we know that for limits and differentiation and integrals now, constants get copied, and then you do the rest of the problem on whatever function, right, you have. So this is what we have for definite this is what we have for what we call indefinite integral. Now, definite integrals are going to be different. And in order for us to get there, we first have to get through some derivations and calculations that we need to... What happened over here? I think, yep, we swapped to less. Okay,
so indefinite integral, that's one where the value of...
Indefinite yeah, well, this is indefinite integral, and we'll see the definite integral will have some numbers over here, and we'll calculate certain stuff. We'll get there. All right, so that was from 4.9. In 5.1, you learn to approximate area under the curve. So we have some kind of a function f of x, and then we had these rectangles we made between A and B, and these were x0, x1, x2, x3, and then we were able to to approximate the area delta x on each one of these widths.
What value it's greater than, but I find a set of values that is greater than, but one that's less than as well.
Yes, so left and right approximation. So we were able to find that if you multiply function at some value xi, because we have the counter over there, x0, x1, x2, x3, that's a counter I, that's 0, 1, 2, 3, right? So if I write xi, I in the index, that means it's x0 and x1 and x2, x3 times delta x. So this represents a single rectangle, and then we add them all up to how many rectangles we have. And we have our, starts at 1. And we have our area approximation. So these are the two concepts we covered so far regarding the latest unit we are learning for calculus. And now we are moving in 5.2. And in 5.2, we get to calculate. So in 5.2, we calculate exact area. So we calculate exact area in 5.2. Now, to get there, we have to develop a formula for it. And that formula, in this case, is going to be obtained by looking at this picture and just, making some connections here. So what I'm going to have is, again, let's do it like this, function f of x, and then I'm going to go and draw, let's say, these three rectangles from A to B. Now, we did write the formula last time, and this formula is important for us. that delta x is equal to b minus a divided by, very good.
By n, right?
Yes. N is the number of rectangles you're going to use. So in this case, as you can see, we're using 3 rectangles.
Right,
so we have that. Now, remember what I said. Whether you're using left points or right points doesn't matter. If you're using left points, we are going to go to each rectangle, and from the left point, we're going to draw the line, and that is going to create these 3 rectangles. And we see that these 3 rectangles are not doing the greatest job of approximating, because there is a lot of error in these in this area, in this area, in this area. There is error there, right? So question is, can we do better? And we said yes last time, right? What did we say yesterday?
We can make more rectangles.
Make more rectangles. So we can, let's say, subdivide each one of these, right? And now if you draw the left rectangles for the new ones as well, you see that you eliminated these ones that I put the cross in, right, the x's. We eliminated those as error. So yes, we have more calculations to do. We doubled the amount of calculations, but we also lessened the error. Now, can I make this better? Well, the answer is obviously yes. Because now if I go in and I divide each one of these, let's say in half, by adding even more rectangles. So this doubles the previous calculation, or quadruples the first calculation, but we have less error still, because now when you draw these left points on top, this and this and this and that, none of these are included in error anymore. So the more you divide, the more error you kick, and you have area which is better approximation to what you want. So now all of this that we have done so far is contained in what we learned in the last class, 5.1, because it's all controlled by this n. If I start with 3 rectangles, then n is equal to 3. If I decide to divide each one in half, then n is 6. And then if I divide each one of those in half, well, then n is 12. So there is really no benefit of this currently. There's no new formula. Sorry, there's a benefit. There's no new formula for this using, we can use the old formula, right? But what's the benefit of this idea? Well, the benefit is that if you keep dividing this and you keep dividing it forever, you are going to run into infinitely many rectangles that are infinitely thin. And each rectangle fits under each of the points of the graph, covering the entire area. And since they have no width, they can create the width that would create the error. So they all fit under it, and they extend exactly up to the function. And because they have no width, they are infinitely thin, they will cover all of the area, and that has to give the full area. So now the idea of what I just told you is this. You calculate area of any single rectangle, right? You calculate the area of any single rectangle. And then you add all of the rectangles you have. You have some finite number of them. So this formula is your formula from last class. And now you send the number of rectangles to infinity because you want to calculate what we now know as exact area. So this formula is developed through this logic that if you divide infinitely many times, you are going to have infinitely many rectangles that are infinitely thin. Now, thickness over here is measured by what variable in this expression? What measures the thickness of each rectangle? Delta x. Very good. Now look at your formula for delta x. Do you see that it's b minus a, which is always some kind of number, divided by infinity? What happens when you divide a constant by infinity? Goes to 0, right? So you see that they are infinitely thin because the thickness is going to 0. And then you also see that since n is going to infinity, you are going to have n as infinite amount of rectangles. Yeah. So what I said, infinitely many rectangles, infinitely thin, right? Infinitely thin. So now the question is, can we use this to compute area under the curve? Well, of course, this is the formula for it. So we're going to use this formula to compute exact area under the curve. So let's take a look at area under y equals 2x squared minus 3x plus 6 from 1 to what? 1 to 6, thank you. I couldn't think of any of the numbers. We don't actually care in this case where yes, you can find in this case minimum, right? You can find the minimum, but currently we don't care because we want to compute the area. We're not looking for the vertex, so we're just going to solve this. So what do I have? Well, first off, I need to find delta x. That one is easy, right? Delta x is equal to b minus a over n, and that's going to be 6 minus 1 over n, which is 5 over n. Note that no one told you number of rectangles, right? Because we are using infinitely many rectangles. So you don't have an n to plug in. Your delta x is just 5 over n, and that's it. Now, the next order of business is to calculate this xi. Now, xi is a plus I delta x. To understand this, we can draw the partition. If this is your A, and then you have delta x to get to x1, and another delta x to get to x2, and another delta x to get to x3, and another delta x to go on. Your A is x0 technically. So to find x1, your I is equal to 1. And x1 is a plus 1 times delta x. Well, a plus 1 delta x gets you to x1. So this formula makes sense. So you have your delta x formula, and you have your xi formula here, which would compute locations at which we are computing for the function. So now, in our problem, xi is equal to 1 plus I times 5 over n. I have to stress this over here, and I'll just put the arrow. I is a counter, not complex. You remember the imaginary numbers?
Yeah.
So I don't want you confusing those things, because I've seen students put all kinds of stuff because they're not paying attention in class. They don't watch the video afterwards, and they glance upon it, they see I, and then they think it's complex numbers and stuff. No complex variables, no complex numbers in calculus 1, 2, or 3. I, in this particular calculation, is a counter that takes values 0, 1, 2, 3, 4, 5, 6, 7, integer counting values. So this is not a complex I, it is just a counter, 0, 1, 2, 3, 4, 5, 6, and so on. So now I have xi. I know how much xi is. I can finally compile f of xi, because I have the formula for f, and I have what xi is. So put them together. Let's use blue to circle two equations that we are going to look at. So this is going to be 2xi squared minus 3xi plus 6. Now you plug in everything and you distribute everything. So 2 times 1 plus, you can say 5i over n, everything squared, minus 3 times 1 plus 5i over n plus 6. So we replaced all x's by xi's, and each xi is 1 plus 5i over n. Now we use ton of algebra to clean this up as much as possible. You will apply the square, and then you will multiply by 2. 1 squared is 1 times 2 is 2. And then first times the second doubled would be 10i times 2 is 20i over n. Plus the last one squared is 25 times 2, 50i squared over n squared when you square. So that's the square of binomial, right? Your pre-calculus. Square of binomial. First, so a squared plus 2ab plus b squared, and you have to double each one because of the 2 in front. So we did that. And then the next part for us is to just distribute negative 3. So we have negative 3 and negative 15i over n, and finally plus 6. So now all of these will combine. I'm going to put 50i squared over n squared first. I can combine the two terms that have I over n. So that's going to be plus 5i over n. And finally combine 3 of these numbers. So 8 minus 3 is plus 5. Yay! I have my f of xi. So what you have seen is the prep work for us to set up the problem. We had to, in order for us to set up this limit, the formula, right up there, we needed delta x. And then for f of xi, we had to figure out the xi first, and then use that xi in the function to calculate f of xi. So now that I have both of these over here, I just need to plug them in and then work out summation and limit and all of that stuff. So now, plug in f of xi and delta x into the limit formula. We have that exact area is equal to the limit n goes to infinity, summation I goes from 1 to n of, and I have now in parentheses 50i squared over n squared plus 5i over n plus 5, and then times my 5 over n, which is the dx we had. Now this is a great moment in time to welcome you all to Calculus, and wish you a pleasant stay, I guess. I don't know. The first order of business is to clearly distribute this one. That's the first cheap, easy thing we can do. Copy the rest of the stuff. So now we have 250i squared over n cubed plus 25i over n plus 25. Oh, sorry, 25i of n squared, 25 over n. Before I get my eyes scratched out. So that was distribution. Now, we had the formula last class where I said that the sums can be separated into individual sums. Remember how you can differentiate each term, you can integrate each term separately, you can do the limits separately. Well, you can do the sums separately. So you will start with the limit n goes to infinity, and then in these brackets you are going to give sum to each one of these individual terms. So summation of 250i squared over n cubed plus another summation of 25i over n squared plus summation of 25 over n. Great. Now, observe, this is important, guys. Just like you know how your limits, and you had age goes to 0, and then you ignore x's because age was the variable that was impacted by the limit, right? Well, you have the same thing happening here. You have I and n, right? Which one is impacted by the formula? Oh, that was a trick question because summation gets both of them. So, I is the variable because you can see that I takes the values from 1 to, right? So I is the one that it's a variable, and 250 over n cubed and all of the other ones are all considered as constants. So we can kick them in front of the sums. So we have now 250 over n cubed summation I goes from 1 to n of I squared plus 25 over n squared summation of I goes from 1 to n plus 25 over n. See, we kick everything outside so 1 stays inside. I goes from 1 to n. So we kick the constants outside. And now, on page 345, 345, Pythagorean theorem, Pythagorean triplet for a triangle, 345. Page 345 has those 4 formulas on top, where they show you that if you just have a constant, you pick up n. If you have, well, they use k, I use I, same thing. If you just have I, then it becomes this formula for triangular numbers. Proofs don't matter now. So n plus 1 over 2. If you have I squared, and we do have I squared, then it's n plus 1, 2n plus 1 over 6. And then for I cubed, we don't have I cubed in this problem, but if there was one, you would have the formula of n squared plus, right? So now we are replacing all of these sums with their equivalent formula. And then this becomes a basic chapter 2 limit. We are done in next 2 steps. So this entire thing over here of I squared, right, becomes n plus 1 and 2n plus 1 over 6. Then we have plus 25 over n squared, and this one over here becomes n plus 1 over 2, and then plus 25 over n, red, let's say. This one just becomes n. So as you can see now, no more right? No more sums, no more i's, it's just n's, and the limit of n goes to infinity. And this limit is particularly easy because all of your exponents have the same order. So you're just looking at the front coefficients. You see, you have on top, you have n, and 2n, right? That's 2n cubed when you multiply it out, right?
Sorry, what was that?
You have n, and 2n.
Yeah.
When you multiply them all together, you have 2n cubed. So 2n cubed times 250 is 500 n cubed over n cubed, and these guys cancel. Plus, oh, we don't need the limit, sorry. Plus, over here you have 25n squared divided by 2n squared. N squares cancel. And finally, these guys cancel, you just have 25. Now, the other terms in multiplication don't matter, because if you keep foiling, you will get the lesser terms as well. But none of them matter because they will always have higher degree in the denominator, and that one will be killed by the limit. Each one of those will go to 0. We know that any value over n to any power goes to 0 as n goes to infinity. That was given to us in chapter 2, that limit. So we don't care about any other term other than the front term with the highest exponent, which is why I am ignoring plus 1, I am ignoring plus 1, I am ignoring any of the cross terms in multiplication. I only care about front coefficient term. Yes?
What about the 6 on the bottom in the first one?
I forgot 6, so I will add 6. Yes. Any other questions? All right, so now 506, they cancel down to 250 over 3. I have plus 25 over 2, and I have plus 25. The common denominator here, it's a 6. So I have 500 plus 75 plus 6 times 25 is 150. Adds to 725 over 6.
And that would be
Exact area.
units cubed.
Units cubed.
Units squared.
Yeah, units squared. And that's exact area. little bit convoluted, but straightforward. Let's go through the whole procedure one more time. You flip your pages back. So we start this calculation by first looking at the formula up there, which we defined through that. Looking at the formula, there we go. So the formula has delta x, formula has f of xi. We have to get those first. So delta x had the formula which we learned yesterday, b minus a over n. Your a and b are given as 1 and 6. Plug everything in, it's 5 over n. We do not have number of rectangles because number of rectangles will be infinity. Therefore, we have nothing to plug in for n. In 5.1, you get n is 4 or n is 6 or whatever, and then you just plug that in. And
So you can't plug that in because then the value would be under 5.
well, no, we don't plug in n because we don't have it. It's going to go to infinity. Now, xi is every location on the partition. Xi is every location on a partition. I is the counter, 0, 1, 2, 3, 4. So the first location is 0, I is 0, I is 1, I is 2, I is 3, and so on. So to get from first to any other location you want, because you need to multiply them all by delta x, you have to keep adding the appropriate amount of the x's. So, to get to the first xi, you will have the x0 plus 1 delta x. To get to the x2, you have a plus 2 delta x's. So you see that this one quickly picks up I, because that I becomes 1, 2, 3, 4, 5 as you want to reach any destination. So now, we calculated delta x, and we finally have xi, because a is given as 1, and delta x is 5 over n. So we also have xi. And the final thing we have to do as a setup for the problem is to calculate f of xi. Now, f was given as this was a minus here, and so it was given as this polynomial. And when you have f of x, then it's all of these are x. If you have f of xi, each one of these is xi. So we are replacing all of the xi's with what xi is. And then you just massage it with algebra until you get the bottom equation. So you just square the binomial over there, multiply by 2, distribute -3, combine like terms. So all of the basic algebra that needs to be done to come up with a 50i squared over n squared plus 5i over n plus 5. So finally we have f of xi, we have delta x, and we can plug those two in the formula, and this is what we get. Now once you are in the formula, you have the limit, you have the summation, you have your f of xi times dx, distribute dx, separate the sums, kick the constants outside, and then use those formulas from the book to get rid of all of these summation symbols and turn them into these terms. And then you take a look, that's a 250n and 2n, so that's a 500n cubed over 6n cubed, and times n squared, 25n squared over 2n squared, and 25n and n. All of the variables cancel, and we just add the remaining fractions. 725 over 6 is what we came up with the calculation, if we haven't, or if I haven't made any mistakes in this calculation. So this is the way to calculate the exact area using what we call Riemann sums. Riemann was a German, one of the gods of mathematics from Germany back in 1800s, and he is the one who figured this out, and technically this is what allows us to have a lot of different technology today.
What did you say the Riemann sum was again?
Riemann sum is the formula that was,
For
yeah,
exact area?
yes.
Alright.
So that is, that's the way to calculate exact area. Now, I change the polynomial, or I put cubic, or I put the linear, or whatever, right, I put in there. It goes the same steps, it's just the calculations are either more annoying or less annoying. You can't make this harder or easier. You can just make it more annoying or less annoying, right? That's the way it goes.
So, remind me, how did you substitute for the I values again? Finding the sums of I.
What I values? We never found any sums of i's. We replaced them by the formulas.
Right. And using those formulas, you just are available in the textbook?
Mm-hmm.
Okay.
That's the one that are on the top over there.
Yeah, you showed us.
So it was like swapping a part on the car, right? You take the part to put the new part in. I think I know what you want to ask, and then maybe we're gonna wait with that question just a little bit. I remember how I read minds.
You know.
Yeah, I do. So, So it's scary. How scary? Yeah, I know. Please write your question down,
Okay.
and I will tell you what it is as soon as I'm done. So now, what we are going to now we're going to switch the gears a little bit from this carpal tunnel inducing calculation into an integral, and compute an integral for the same polynomial that we had up there. So the integral was for 2x squared minus 3x plus 6, I believe. Was that correct?
Yeah.
Right? And here is the part of the new notation, guys, for you. We had a range from 1 to 6, and those become the numbers on the integral, 1 and 6. Are we all green? Now, we are going to calculate this integral the same way we calculated in 4-9, and then we will deal with 1 and 6 at the end, when we are done with integration. So, what is the integral of 2x squared?
See how it's times x to the third of 3.
Yes, 2x to the third over 3. You will copy 2, that is you will copy the 2, that's the coefficient, right, the constant you copy, and then integral of x squared, you have to add 1, so it's x cubed over 3, right? Good. What is the integral of 3x? Perfect. Plus, an integral of 6 is 6x. Now, remember how you used to put plus c plus every time, right? Well, not now. Now we put a vertical line and we put 1 and 6. This vertical line is read compute at 1 and 6.
That's 1 and 6, not 1, 2, 6.
1 and 6 as the numbers. Now, the way this works, and I'm going to write the formula later, is you go through the entire answer you have over here, and you plug 6 everywhere, and then you subtract the same polynomial with plugged in 1 everywhere. So, it's going to be like this, minus that, and you will be placing this polynomial with 6 plugged in and then with 1 plugged in. So we have 2/3, 6 cubed, minus 3/2, 6 squared, plus 6 times 6. And then the next one is plug in 1. 2/3, 1 cubed, minus 3/2, 1 squared, plus 6 times 1. And now we compute this monstrosity. Now, I like to use algebraic tricks to compute rather than the calculator. You are welcome to punch all of this in the calculator and get a number at the end. I like to use clever tricks because I'm lazy to use calculator. So what I'm going to do is, you can completely ignore what I'm going to do. I'm going to peel off one of the 6's from 6 cubed and have this as 2 times 6 over 3, and then have 6 squared minus 3/2 times 6 squared plus 6 squared. And then minus, these ones don't matter, so 2/3 plus 3/2 and then minus 6. I can factor out 6 squared, which is 36, and in parentheses, when I cancel this, I have 4 minus 3/2 plus 1. And I can deal with, well, I'll deal with everything at once. So this is just me being lazy to get the calculator. 4 minus 1.5 is 2.5, 3.5, that's 7/2. So 36 times 7/2 minus 2/3 plus 3/2 minus, you can put 6 over 1 if that makes you smile. Common denominator is 6. So I have 36 times 21 minus 4 plus 9 minus, is that 36? That's 36. Great. Nice. 36 times 21 minus 36, that's 36 times 20. Plus 5 over 6. 36 doubled is 720. You don't need to follow any of this. You can use calculator instead. I'm just lazy. So 725 over 6. Did we just discover a shortcut?
Yeah.
You know when you go to the eye doctor and the eye doctor goes, what's better, A or B? And then they keep switching, right, until you faint.
So, what's the point of the first one if we can just do that?
Oh, the first one is the way it's actually mathematics in the background. This one is the hack way.
So that's why you make the list.
So we can do it, so it's like,
It'll still,
That was your question.
it'll give you the same result.
That was your question.
so we can do it either or.
Yes, I prefer if you do this with the integral.
Is there any situations where that won't work?
No. You remember how you learned the limit definition of the derivative and then you learned the shortcuts in chapter 3? Well, here is your limit definition of the integral, and then you learned your shortcuts actually in 4.9. And this is the part of the class when everyone goes, "Whew," right? Is it? Yeah. So how many of those sum problems should I put on a test so everyone is happy? 1? Who said 1? Someone's gonna get the tire slashed.
That's true. If there's like 10 questions, put like 10.
Oh, 10.
Of the summation questions?
As long as they're easy.
10 of the... I asked about summation questions. You said 10. Someone said 1 in this area, I'm not sure who.
We can do both.
We can do both. Yeah, keep digging the hole deeper. Reminds me of my first job when I landed in the US. Said, would you like to work? Da. Well, I didn't know about yes yet. So this Polish crew. We meet Derek over here, and Derek is going to give you some work and they're going to pay you $8 an hour. Yes! Dig 1 foot hole, and then we're gonna plant the tree. First time holding the shovel. I have no clue what 1 foot is. I'm metric, okay? So, right, he went to do stuff. Came back, I'm halfway to my waist in a hole that is like enough to make a pool, like jacuzzi. He goes, no! The whole yard ruined everything, like grass and dirt everywhere. So, yeah. Well, that was my day 3 in US. Anyway. Let's do more of these. What we just discovered, guys, is that the exact area is given by the formula limit n goes to infinity, summation I goes from 1 to n of f of x I delta x, which is at the same time the integral a to b f of x dx. This is the focus of 5.2, and since we learned in 4.9 all the shortcut formulas for integration, we don't have to compute the limit sum problem. We can just go and compute the integral instead.
So you said this would be the better method.
Yes.
Using the integral.
Now, the most important thing here is to write the formula for the definite integral, because that calculation that I did, I said plug in 6, plug in 1. Well, let's write let's write it this way: a equals integral a to b of f of x dx is equal to capital F of b minus capital F of x computed from a to b f of b minus f of a. This is the formula that you are using to calculate area under the curve. So use this to compute area under the curve. Use this to compute area under the curve. Cool, huh? Now, if you are able to integrate, hopefully you'll be able to plug in the numbers and compute the value at the end. There is a pitfall though, we'll cover it, but the calculation should be straightforward. Let's say you have function y equals e to the 2x from ln2 to ln6. So you know what to do. A equals integral ln2 to ln6. Those are your limits. ln2 and ln6 are numbers. Nothing special, right? And then you are supposed to integrate e to the 2x dx. Now in 4.9 you memorized that e to the ax is integrated into e to the ax divided by a, right? So this becomes e to the 2x over 2, computed from ln2 to ln6. Now your job is to plug in the limits. The upper limit is b, it goes first. If you look at the formula above, right, you will plug in b limit first, and then you will plug in the a limit second. So we have e to the 2 ln 6 over 2 minus e to the 2 ln 2 over 2. To compute this, the 2's in front of ln's will go inside as powers. So e to the ln 36 over 2 minus e to the ln 4 over 2, which would give you 36 over 2 minus 4 over 2 when ln and e cancel, to get 18 minus 2, 16. Area under the curve, area under e to the 2x between ln 2 and ln 6 is exactly 16. Cool, right? I know. It's awesome. Let's compute one more, and then, well, few more, not one more, few more. So how about if y is equal to 2 over x on the interval 1 to 3? What's the area? Y equals 2 over x. There's a question in Discord. 41 messages.
This is another homework
You're on the
problem.
Discord.
Oh, spicy.
Was she right with her answer?
Yeah. I'm gonna end it.
Where is this question?
All right. Area is equal to the integral from 1 to 3 of 2 over x dx. Was that a U-Haul? Was that a U-Haul meme?
No.
No?
I was showing her the Discord.
I know. Yeah.
Yeah.
It's in this. All right, so what do we have, guys? We kick 2 outside, 1 over x dx. And what is the integral of 1 over x?
ln absolute x.
ln absolute x, computed from 1 to 3. We plug in 3. We don't need the absolute value because positive numbers anyway. Minus 2 times ln of 1. Now, how much is ln of 1? Excellent. So the answer is 2 ln 3. And if you want the boss, right answer is just ln 9. Because the 2 goes in as the exponent of 3. 3 squared is 9. But that's the, you know, what they would say on the internet is thug life, right? So that's the boss answer. All right. How about trig? You love trig. So how about y equals sine x on 0 to 2 pi? Remember, this calculates area under the curve. What is area? Is the surface that you can color, right? You take crayon and just like, I've been doing it lately. It's so nice. You know what I mean? I'm gonna post something of that work on that. I'll do it for myself.
I'm just laughing at how my math lab is.
Oh yeah. Yeah, I had the first thing in my top 2 class in the last semester was the first week. I had a meme contest because it was one of those same expressions we're talking about.
Yeah.
And said, well,
Well, I think it's stupid. Like, I think the variables too. Like, if you use the wrong variables, they might be wrong.
yeah.
It's like, but I'm not wrong though. Oh wow. It's funny because I would get Starbucks. I mean, it's not like the same way that you need kids, but that's why. Yeah.
This one?
No. No. Isn't this great? Isn't this just this is crazy? Yeah. Because yeah, because cosine is 0, there's no. But how 17 ties into 7? So is it just 0? But this is positive. So
How's it going? Done? Did you get 7? Good, because then we're wrong. What'd you get?
I got 0.
You got 0? You got 0. You got 0, and you got 0, and you got 0. Right? Now, I am 100% sure that you calculated this right. You got 0, but you also know that 0 is wrong answer, right? So what just happened, right? What happened? Because independently, at least 7 people here, 8, 9, whatever, right? Everyone calculated 0, everyone checked with people around, and all of a sudden, right? Apparently everyone has a 0, but you know it can't be 0, because you can draw the sine x graph, and there is a part that you can color, right? So you know 0 is wrong, and you will have to argue that something has to be done to fix that. So if I draw the sine graph from 0 to 2 pi, I can clearly color, and if I am able to color, that means it has area. Well, what's the issue? You can see that the sine x has 2 bumps. One is above, one is below x-axis, and they're the same size. The bump that is above x-axis carries positive area, and the one under x-axis carries the negative area. And when you add them together, what happens? 0, right? Now, is this something that has its use in the world? Of course. As I said, most of the stuff we know about in physics, and it depends on these things. Energy is area under the curve, and you do have positive and negative energy, right? And when you add positive and negative energy, they add to 0 if you have the same amount. You can cancel magnetic field. You can cancel electric field, right? Can't cancel gravitational field, right? It's the one that doesn't have its opposite. But when you look at this, it's an issue. So what do? Well, we have to be mindful of functions and graphs. For area under the curve, anytime graph dips below the x-axis, we have a problem. And we have to isolate that part and slap the absolute value on it. So I cannot compute this as sine from 0 to 2 pi. I have to compute this integral as sine x dx from 0 to pi, that's the red one, plus the absolute value of sine x dx from pi to 2 pi. And now when you go through your calculations, the answer will be 4. Exactly 4. And it's going to be awesome. So it is good time for you now to go and write down the sentence, right? The paragraph or whatever, where you explain to yourself in your words that you will remember, because it will mess you up if you don't know it. Any area below x-axis needs to be in absolute values. Because if you just calculate, it will be negative and you will have the same issues. So any area under x-axis needs to go into absolute values.
0 is the wrong answer.
0 is the wrong answer because, look, I colored. You see the red and the blue, right? So there is area in units squared that it's covered, right? If we were able to integrate circle easily using this method, you would then say that the integral of a circle is 0 because upper and lower half, right, would cancel each other. And you know that the area of the circle is not 0 because the circle is there.
How do you get 4?
Yeah, wouldn't it be 2?
No.
So that,
How do I get 4? Like this.
Okay.
I just compute this. Integral of sine is negative cosine, and I plug in values. And then I get 2 from this one and 2 from this one, and when I add them, it becomes 4.
Yeah, where do you get 2 from?
Wouldn't it be 1?
Yeah, isn't it 1?
Cosine of pi is 0. Negative cosine of pi is 0. Right?
No, it's negative 1.
I think
This is the time when you facepalm.
Oh,
All right, so patience, young Padawan. Negative cosine x from 0 to pi plus absolute value of negative cosine x from pi to 2 pi. Negative cosine pi minus negative cosine 0 plus absolute value of negative cosine 2 pi minus negative cosine of pi. Negative cosine of pi is negative 1. Negative and negative is positive. Cosine of 0 is 1. Plus absolute value of negative cosine of 2 pi is negative 1. Minus and minus gives me plus, but cosine of pi is negative 1. And then absolute value. Negative and negative gives me positive, which is 1. Plus another 1. Plus absolute value of negative 2 is going to be 2 plus 2, and that's equal to 4. Yay! Now, obviously, on the lab, you will have plenty of opportunity to enjoy area under the curve with a twist, right? Up and down and up and down, up and down. All right, so now we need to talk about some rules and regulations and properties and things like that for definite integral. First order of business, and the one that gets me really, going is notation. You have integral a to b of f of x dx when you have, right, let's say a single term. But if you have multiple terms, then you are going to have f plus minus g dx. I'll write it in blood. Note the use of parentheses with 7 exclamation points. They are not there for decoration. If you paid attention earlier in class, you know that your limit of the sum of f of xi delta x is equal to the integral f of x dx. Didn't we establish back in differential section 4.6 that dx is equal to delta x? We did, right? So that checks off. What is this? Well, that checks off as well, which means that these two are squished into this symbol, right? Great. So do we all understand that? Great. So now we have this one-to-one correspondence. Now look at this. What is the symbol in between these two? What does this represent? Area of one rectangle, right? It's the height times the width. So what do you have in between? You have multiplication, right? This thing, that drop of blood over there, you see, that it's a grade killer, is multiplication. Well, if you have a correspondence between these two, there's a multiplication in here as well, which is why you need these parentheses. It is dx distributed to both of these to do integration, right? So what's the highest tier allergy I have when you don't put dx? You killed integral completely, because at that point you say, oh, area of the rectangle is height, because you killed the width. You didn't put dx. Dx is the width of the rectangle, right? If you don't put dx, you don't put dt or dr or whatever the hell you have there, well, you don't have the mathematical concept working at all. It's not there for decoration. It's there to represent the length of the rectangle, because the rectangle that you are looking at, that long strip like that, has delta x on the bottom, which is dx, and the height of that one is f of x. So when you have f of x, and you have to multiply it by dx in order to have an area. So placing dx at the end of every line that has integral is not optional, because if you don't put it, you are ruining the concept of an area fundamentally, right? So no complaints when the points are taken per line for any expression that has no dx in it. Yes?
So if you separate the integral, like if you have multiple terms, you use the integral per term, you use dx per
Dx per term. Integral per term, dx per term. We're going to spell out those formulas so we know exactly what's happening. So this is, guys, for notation. Multiple terms with pluses and minuses, you need to use parentheses because dx needs to distribute to each one. Now, you can't cut corners. You are making even worse mistake if you don't put dx at all, because you are killing the concept of an area completely. Now, the formulas that help us survive over here. of f of x plus minus g of x dx. Observe, I put the parentheses because I have multiple terms, whether they're terms or functions. I put the parentheses because dx needs to apply to all of them. And then we have integral of f of x dx plus minus integral of g of x dx. So each one gets its own integral symbol, each one of them gets its own dx. And then you have the overall area is equal to the first area plus minus the second area. Now we're going to add a and b everywhere. So go ahead and add a and b on all of these integrals. Now, there are three other formulas that are really cool. There's a formula which says that the integral of f of x dx from a to a is 0. Why? Good. I like all of the answers you provide. You gave me different answers and I like them all. Some of you said you have no width. Yes, exactly. I have no width in this case because your delta x, which is your dx, is b minus a over n. And if you have a minus a over n, that's 0. So if one of the lengths of your rectangle is 0, it's dead. And someone else in the group also said, well, you would have f of a minus f of a when you do the formula. Well, that's the same, so that's 0. So whichever way you like, right? Personally, I like the answer with my function has no width, right? There's no range to calculate because when I have function f of x, I should have a and I should have a different number as b so I can have area. If I just have a like this, well, there's no area there. It's just a vertical line. There's no area to infinitely thin line. So that's that part. Next formula pops up again in our 5.5 section, but then pops up constantly in Calc 2, Calc 3 differential equations. Do yourself a favor, remember this thing. You are allowed to swap a and b in the integral as long as you put the minus in front of the integral. So if you want to switch a with b, and in some cases you will have to, I mean you don't have to, but it's nice to do it, you have a minus integral b to a, f of x dx. When we do u substitution, your old limits, let's say 0 to 1, will become new limits 5 to 3. And you go, well, smaller number is on the top, so let me just swap them. And when you swap them, you have to put the minus in front. And finally, the formula which allows us to calculate area of the under the curve if you have to split the integral. Now, I'm going to write this and then I'm going to draw the picture to show it. So we start by f of a to b of f of x, the integral, oh my god, integral a to b of f of x dx is equal to integral a to c f of x dx plus integral c to b f of x dx. This one, you have to say that c is in between a and b. Now look at this. Here's the picture that explains what happened. This is your function f of x. Here's your a, and here's your b. Do we all agree that area under the curve is all of this shaded region between a and b? Are we all agreeing on that? And that's what this calculates. Right? Now, you are allowed to come up with any value C between A and B and make the cut anywhere. Now, what happens here is you come up now with two separate areas, and you can just add those two separate areas to get the large area. Can you do it more than once? Sure. You can cut this 29 times if you want. You just have to sit there and calculate, right? So you can cut, and that's going to be beneficial. Obviously, we used it already for the sine. I did cut 0 to pi, and I added pi to pi over 2. So my C, for the problem with the integral of sine, my C was pi. Yes?
I think you answered my question.
Well, remember how I read the minds, so...
I was going to ask in what situations would you use that, but that's kind of...
Yeah, it's exactly that. That's the formula. This is the one, so you just add absolute values if they flip below. Exactly. Everything.
So this is basically the mean value theorem of integrals.
It's a little bit different. It's coming up after the exam. That one. Mean value theorem integral form will be presented on Tuesday after the test. All right, so time for the break. When we come back, we are going to talk about something mildly important, fundamental theorem of calculus. Nothing special, all right? See you in 215 seconds.